Hello, my name is Daniel Evans, and I thank you for joining me on this presentation of conference paper of the same name. Just to start off with a little introduction, I earned my Bachelor's of Science in Mathematics at Pensacola Christian College back in 2010. It was there I discovered my love for English and also earned the English minor. I've been in the IT world for 5 years, working between network operations, system and network security, and IT project management. And during that time, I obtained my CISSP in 2018, and now I am working on obtaining my Master's of Science in Cybersecurity from NYU Tandon, starting off my first class now and looking to graduate in 2023. So let's dig in. We're going to start off with the problem we're trying to solve, look at current solutions, what's wrong with those. We'll talk about our alternative, go into the definition, our hypothesis, testing it, failing in a few places, but looking at what other evidence we have before we conclude and look at for future work. Now the problem is simple enough. How do we reduce spam on the internet? Anyone who's been online the past couple of decades has received some form of spam. It could be in unwanted messages or advertisements from some sort of fake persona online through Facebook or Twitter. For phishing, it could be someone trying to get you to click on a link and hoping to compromise your computer. And on a larger scale, it can even be a denial of service where you can receive thousands of fake messages and it will drown out the real information that you want or need on a given platform. This problem has become worse thanks to bots or just automating these kinds of repetitive tasks. A bot can take on some sort of persona, getting multiple accounts on platforms, and send out mass amounts of spam. You can have thousands of bots creating, for example, the altering public opinion. If you have thousands of tweets coming from what appear to be legitimate people, but are actually bots, then they can have an effect of influencing the perspective on social media. And in a similar fashion, bots in the thousands could generate revenue through extra clicks, likes, or other actions that they can take on social media platforms. For example, this video here, picture I show, is of a Tom Scott video. He created an API that will allow this interface loads up the YouTube video. It reads how many views the video has, and then it renames the video with that number of views. And so the title always has the correct number of views listed. And while such a small amount of code creates a very awesome effect, it has a secondary problem, and that is how many of these views were generated through that API itself. If over the course of a month, this API renamed the video one time every second, then just a little short of 3 million of these views would be created from Tom Scott himself through his API, through his bot. And so we see even well-meaning bots can create problems through their use of spam. To understand how society has responded to spam, we have to do a little history. Starting off with back in the late 90s, a couple fellows created the completely automated public Turing test to tell computers and humans apart, also known as CAPTCHA. This wasn't popularized until 2001 when PayPal instituted it for their account registrations. And then when we see Google in the late 2000s bought the reCAPTCHA service. They started using the text CAPTCHAs, and in 2012 introduced image CAPTCHAs, as we see here. And then in 2014 we see Google implement the no CAPTCHA reCAPTCHA, which is where things start to get a little bit invasive. You see this CAPTCHA worked by looking at how your computer is responding to clicking on the I'm not a robot. It's checking mouse movement and possibly looking at other files in your browser through its cookie. In 2017, this I'm not a robot check mark went away as well in what they call an invisible reCAPTCHA. You don't even see, but you are being checked for human indicators, which, as we would assume, come through your browser, come through some sort of token that Google can monitor in order to say yay or nay that you're a robot. And then finally, the most recent changes come in reCAPTCHA version 3. If you look into it, there's a lot that shows that they are doing continual monitoring. They want the most context about interactions with every site that implements reCAPTCHA version 3. And they say that they recommend including reCAPTCHA verification on forms and actions and background for analytics. So we can see reCAPTCHA is pretty much always on. If it's on the website, it's monitoring you in some sort of fashion, trying to learn from how you're acting and using that data in order to improve itself. But also, that data could potentially be used against you, especially if, say, Google was hacked or if there's an insider. There are privacy concerns here, especially if it's always monitoring everything you're doing online. So the question becomes, if we're a website and we don't want to use reCAPTCHA that is continually monitoring our customers, what other options do we have? In 2012, a concept was posed as another form of Turing test called the Winograd Schema Challenge. In this test, there is a sentence. There are two subjects, two parties in this system that share the same pronoun. If it's a he and a he, him and a him, she and a she, it and an it, they and a they, so on. And somewhere in this sentence is that pronoun. The user must resolve the pronoun to one of those two parties. And this requires a sense of some common sense, because understanding how the objects relate to each other in order to know which one is which. And finally, there's a word that swapped out with another word still makes perfect sense but changes the answer. An example here, Joan made sure to thank Susan for all the help she had given. In that situation, we know that Susan would have been the one that had given the help. But if we say received, then the person that had received the help was Joan. Why? Because we know that if Joan's thanking Susan, then that means that she is the receiver of the thanks. When the Winograd Schema Challenge was introduced in 2012, the questions known as Winograd Schemas seemed nearly undefeatable, with most bots coming with a near half chance of solving, a simple guess rate of 50-50. But soon the Kingston Winograd schemas were being shown. In 2015, this is when neural language models were starting to be introduced. Now, the old style, the statistical language models, would look at the sentence structure and be able to make sense of, hey, here's the subject, here's what it's related to, and the Winograd schemas were very good at defeating statistical models. However, with neural language models, we're now being able to tie not just the sentence structures, but also some of the sense of how words are related to each other. And these started to show a higher success against some types. These neural language models are trained on a heavy amount of heavy corpus, a lot of books usually, and able to take a lot of concepts from texts, from real life common sense sentences, to be able to find the relations and solve these problems. And this is where we start to see that weakness in the structures with Winograd schemas. Skip several years, several papers, and several new advancements in the area. And now at this point we see, for example, the Roberta, a specific model that was trained on a very large amount of not just a large corpus of text, but also trained on these kinds of questions, and that's where they started to obtain an 83% success rate. And the most recent work I've seen, the Winograd in 2019, was another question set that after training Roberta on that, we were seeing them defeat the Winograd Schema Challenge with a 90.1% success. Considering that humans are already only in the high 90s, this was enough to say that the Winograd Schema Challenge was dead. But is the concept of Winograd schemas itself dead? Well, there are very few studies on developing Winograd schemas. One direction we could potentially take it is in ambiguous contexts. So what is an ambiguous context? My definition here is a secondary pronoun that must be resolved before the common sense data or the rest of that context within the sentence can be applied to one of the two parties. In my example here, we'll start with what it's not. When we say Paul shook Mark's hand after hiring him, him here can be solved statistically because we know that we'd be talking about he if we're talking about Paul. So Mark being the object is him. That's not what we're talking about. But as we move down, we say Paul shook Mark's hand after hiring him, but he still seemed unwelcoming because of his tight grip. In order to figure out whose tight grip, we have to talk about who is the he that seems unwelcoming. And in fact, if we switch the sentence and say that he seemed overzealous, the person changes. Paul hiring Mark, we would know that Paul is unwelcoming, but then if we switch the word, we think that Mark is overzealous. So in order to answer whose tight grip, we have to know who was unwelcoming or overzealous. This situation, I theorize, is going to be a little harder to solve than your average Winograd schema. And there are multiple reasons this helps. First of all, yes, with having to solve two pronouns now, the bot would have to make additional common sense searches to understand the relations between these pronouns. And that will extend the amount of time for the search and lower the machine accuracy. But there are also other complex portions of the sentence that will add additional resiliency. For example, maintaining subjects that are similar, for example, just using their names instead of giving a type or attributing these subjects some sort of, any sort of parameters that distinguish the two will keep them more alike and make it harder for a neural network to distinguish these two and come up with an answer in any sort of statistic fashion. And so I'm setting my hypothesis that adding these ambiguous contexts will reduce the current language model success rate more than halfway back to the chance level performance. That's what we're trying to get to here. For an example, if we have one model that can crack it at 90% success rate, we're looking at reaching a 70% success rate using just our ambiguous questions. And so now it's time to test, but there are a lot of pieces involved. While I've hinted at a few of them before, we'll go into detail with each one now. Starting off with the question set that we're going to compare to our own work to see if we're making any progress. Out of the existing question sets, I've chosen Winograd Schema Challenge 273. It's a set of 273 questions. It has been a staple and a baseline for a long time, and because of the simplicity of the set, I believe this is going to be the best to be able to do a side-by-side comparison. Next is, what question set are we going to use to support our hypothesis? And I have written out a set of 5 question pairs, which means 5 sentences each using a special or an alternate word for a total of 10 questions. For the sake of naming things as everyone else has, I've named it the Rudimentary Ambiguous Context Question Set, or RACS, and we'll go with that for the rest of the presentation. If you are interested in the questions, I do have it as the very last slide, so please take a look. Now we'll get into what is testing our Winograd schema sentences, the language model that will be doing the testing. Now we could look at statistical versus neural, but considering statistical is at this point outdated and inefficient, we do want to go with the times and choose a neural system. There are also considerations of what would be a base versus a large version of some models. And in this case, they usually just refer to the amount of processing that it can do at one time, number of words, connections that it will use. And here are a few options that are available: Glove, Elmo, Bert, and Roberta. With Roberta being the most recent and impressive, that's the solution that we're going to look at for now. But you can't simply just choose a model because the model is the how it will parse the sentences without really what will it parse it with. And so we need some sort of corpus, some set of text that the model will train on. The pre-training here, here's a few options that we have, but if you see there are pre-trained models, and BERT and Roberta happen to be kinds that are pre-trained on a large amount of data. That's what we'll be using today. Additionally, there is fine-tuning. Usually that will be a set of questions that will be that this model will learn from to be able to see specifically how to solve these sentences. It is not necessary, and we're not going to use it for this experiment for the sake of simplicity. That leads us to the setup that you see on the screen. I've also included statistics for the computer here. It's a simple Windows 10 i7 and 32 gigabytes of RAM that does come into play with some systems requiring a minimum of 64 gigabytes of RAM, but we should be able to work with Roberta just fine here. And installing Roberta is a little more complicated than just download and run. There are several parts that will need to be individually installed. Starting off with PyTorch. This is the backbone for the deep learning. It interfaces with the graphics cards and properly manages the memory as well. This is why you have to be able to specify the number of CUDA cores when you download it. In my situation, my graphics cards are not compatible, and so I had to select none. This was downloaded through Conda, or Anaconda, and this and the rest of my Python was run through Python 3.7.6, the type that is used with the current Anaconda distribution. Next is FairSeq. This is the sequence modeling toolkit that trains the models. I still needed it for our pre-trained model because there's still some of the terminology that it uses. And we had to download this manually in order to remove the Sacre Bleu part of the system. This is not compatible with Windows, and also all the Sacre Bleu does is uses tokens in order to develop blue scores, which is a system we're not even using for this experiment. So once we downloaded it, modified, took that part out, and then installed it with pip. Next is Spacy. This was needed for loading Roberta, and actually it's the library for natural language processing. This is actually where we get our commands in order to distinguish the subjects in the sentence. And then finally, Roberta itself. We've selected Roberta.large, probably wasn't necessary, but once again, the large version runs on a larger architecture and would have a higher chance of success. So this is what we consider the leading model at this time. And once we had everything set up, it was time to disambiguate, and this is where we ran into problems. As you can see, actually loading TorchHub, loading Roberta itself went well. The dictionary had that 50,000 types, as it says there, and its next command line here in Python, disambiguate pronoun, including the sentence, that started to run, and then right at the bottom there you can see a permission error. This is an error that's going when it saves to a local temporary folder. It's trying to save it there temporarily, pull it back out, it can't pull it out, and this is something that I'm still trying to debug. In fact, I went ahead and contacted the people that were working on the Roberta, asked my questions about how to resolve this, and my response was this command is a little bit kind of hacky, in his own words. Thanks for Mylot for helping me out here. But this is what I have to work on next in order to take the next step, figure out what's going on, and finally be able to disambiguate our sentences. Unfortunately, it's a lengthy process, and I just have not been able to get it done in time for the due date for this paper, but I intend to continue through, and hopefully I'll be able to update this video and a paper itself with some good details later on. But it turns out we have more evidence we're going in the right direction than just my experiment. Remember Winograd? This question set was developed by crowdsourcing 43,972 questions. After that, these questions were entered into AFLIGHT, and this program algorithmically filtered out most of the questions and left us with 12,282 unbiased questions. When you look at how it filtered out these questions, you see that it would filter out any of the questions that had a strong correlation between the special or alternate word and the context of the sentence around it. Once they did this and they used only the unbiased set, they were found that Roberta could only have a success rate against their question set at 58.9% versus the 83% that Roberta had on WSC 273. But if you don't believe me, look at Winograd's evidence itself. Here's an excerpt from the Winograd paper discussing how AFLIGHT conducted the filtering. The first two questions here were rejected, and you can see they highlighted where there were positive items such as loved and exciting, and highlighted the negatives in red with ignored and dull. And this was able to specifically determine the answer simply from whether it's a positive concept or a negative concept. In the second question, again, they were able to create a tie between beginner and weak and advanced and strong. While the third and fourth question pair there were able to avoid those kinds of situations entirely. By conducting our efforts to create a larger distance by creating these ambiguous contexts, we should be able to accomplish much of the same resiliency that we see in these stronger questions, and maybe even be able to develop more specific rules in order to create better word structures. In conclusion, we're not quite there yet. Our direct evidence testing our questions is delayed until we can debug our Roberta setup and be able to complete our testing on our question sets. However, the set is ready for testing. RAX is ready to fire up as soon as I or anyone else who wishes to conduct this test would like to test out these questions. And if you do, please let me know. My contact information is coming up soon. And finally, there is some evidence that this is going to work out. Winograd does show a correlation between data set specific bias and Winograd schema solvability. And if it's not exactly this form of ambiguity, we know we're close. For future work, starting with obvious, we need to complete testing on our RAX question set and compare that to other Winograd schema data. It can be on the Roberta model or any other model that is still considered modern and useful. After that, completing testing on more models and really more question sets, because we need to see how these correlations are working, and just using the Winograd schema challenge set may have some holes or some other correlations that we are not analyzing with just this question set. Then, once we've determined that we have a positive correlation between ambiguity and stronger sentences, we create those definitions, write them in parameters that a user could understand when writing sentences, and then implement that into a crowdsourcing session, much like what Winograd did to create their question set, and potentially use bias filtering and determine whether these stronger questions can survive at a higher scale and be implemented as a CAPTCHA. Well, this concludes my briefing. I do appreciate your taking the time to listen in for this entire presentation. If you're interested, please contact me at the email addresses below. I'm more likely to respond with my personal address at the bottom. But either way, thank you again. Have a good one.